And now what we want to do is start off then by again um, identifying series and parallel relationships. And so with the source here, as usual on the left, very often it's the right we'll start with. Okay, so let's think about series and parallel relationships over here. This branch containing R6 is in parallel with this branch containing 7 and 8. Before we can tackle that one, we should think about the fact that 7 and 8 are in series over here. Okay, so we'll start with 7 and 8 then. Now, if we keep our eye on the rest of the circuit, you know, there's no series and parallel relationships over here that we can tackle yet, except for this little branch right here got 3 and 4 in parallel. And so why don't we take a look at that one as well before we redraw. Now you might notice, you know, 3 and 4 here, that's in series with 5. You might notice 7 and 8 is in parallel with 6. If you're getting a bit better at these because you've practiced, you might want to tackle all those before you redraw. Okay, now I'm just going to have a look at those two and then redraw. And so I said that our A was equal to our 7 in series with our 8. And so that means then that our A is the sum of 120 ohms plus, got my cursor lost again, I can't see the big yellow circle that goes with it. I'll just see a little tiny dot. And so we have 160 in series with 120 in series with 40, and that gives us our A equal to the sum of those at 160 ohms. Now we also then have our B is equal to R3 in parallel with R4, and so we get the product over sum, or when they're equal like this, we can just take the value and divide it by the number of them. So 100 divided by 2 of them gives us 50 ohms in that branch for our B. So now we can think about redraw. And so I have this, which again now I'm going to copy and paste back to that main page. And make it a bit smaller if I can. And so here we have our redrawn circuit, which shows our B replaced 3 and 4, our A replaced 7 and 8. And so now, you know, it becomes clear, I hope, that our 6 here is in parallel with our A, and our B is in series with our 5. So I said that our C is equal to our 6 in parallel with our A, and you'll notice again that you know, this one has been designed to be easy to reduce because we have 2 equal resistors in parallel, and so we'll take that 160 divide by 2 and come up with 80 ohms for that branch. Now remember that branch contains all of resistors 6, 7, and 8, and then I'll combine our D to say that it is equal to our B in series with R5, and the sum there then of the 250s gives us 100 ohms for RD. And then I redrew it again, and I came up with this. And so Here now, you'll notice that again, right? I have used RD at 100 to replace RB and R5, so that contains 3 resistors now, 3, 4, and 5. And I have included RC to replace R6 in parallel with RA. RC now includes all of R6, 7, and 8. So we're left with this 4 resistor circuit. And our simplification now is R2 in series with RC, right? So these two are in series. Okay, so RE then is equal to R2 in series with RC, and we have 20 ohms plus 80 ohms and 100 ohms. And so I redrew it again to include RE. And so now we have these two here in parallel. So our next reduction, RD in parallel, that should be with RE. And again, all right, 2 equal resistors in parallel. 100 divided by 2 gives us 50 ohms. And so, hopefully by this point you can see that RT now is R1 in series with this value, which I called RF. And so, before I bring in that other circuit, let's say that RT, right, we should be able to see that if we're going to replace this with RF, R1 now, our total current is going to come up here, and it's going to go through R1, and then it's going to go through RF. So RT then is R1 plus RF, and the sum is 50 plus 50, and so 100 ohms for RT. And that was the answer, right, to part A. And so I think we should have probably talked a little bit before now about exactly what we've been asked to find. And I did have that circuit redrawn. And so I'm going to pop that in there now. Just for completeness, I suppose, if anything, if nothing else. So, and now we have RF and R1, and we have RT. So I don't think there's any need to redraw it to show just the 100 ohm resistance, but we do know now that we have the source now will produce the current IT, which then will produce a voltage drop here, V1, and of course VF, and we can bring these back to the previous circuits. Okay, so part B will ask us now to definitely calculate IT, and so I'll usually start off all my examples that way. It's not necessary, I suppose, but Ohm's law says that IT is equal to VT divided by RT. And again, I'll note that VT is not the voltage drop across any one resistor. If there was a resistor directly in parallel with the source, then we would be able to find one of the currents before we started. And you will see that now and then. Not in any of these examples that I've presented, but it does show up. Okay, so we have here 250 volts, so it's a bit big compared to most of the ones we've seen so far, divided by RT, which was 100 ohms. And so that gives us nice even number for current, 2.5 amps. You're concerned about your true significant digits, you call it 2.50, but there's no rounding there, so there's no need to do that. And that is IT, and of course that is the answer to part B. Okay, so now that we've got all these redrawn circuits and so on, let's think about what we've been asked to find. We got RT, we got IT. V4. So the voltage drop across this resistor, right, is V4. And, you know, think about where else that shows up. Well, 3 and 4 combine to make RB. And so that means in this circuit right here, we can say that this VB is actually V4. Because 3 and 4 were in parallel, same voltage drop across them as VB. So we got V4 there. Now, when we combine B and 5, move down to this circuit, we don't have V4 in this circuit. But we got the current in that branch, and that'll be helpful and help us find V4. And whether you call that current I5 or ID or IB, see all of those resistors in the branch, that is the branch current, and we can give it either one of those labels. Okay, what about P6? The power delivered to resistor 6 is this resistor here. And so, you know, the voltage drop, V6, shows up definitely in this circuit here. And so because 6 and A combine to make C, this voltage right here is also V6. Okay, so we can find V6 by finding VC. And so that should be a 6 there. And so now we can, you know, we don't need to go up to this original circuit to find V6. Okay, what about I7? I7 is the current in this branch here, I7. And because R7 and R8 are in series, they got the same current through, they combine to make RA. So the current IA is in fact the current I7. Now when we combine these in parallel, remember that the current here is not I7, but the current here, if we call this IC or I2, right, this current right here is IC. And so if we wanted to do current division, IC breaks down into an I6 and an I7, or an I7-8, whatever we want to call this one. And so, you know, generally we could use current division there. But, you know, if we're just sticking really with Ohm's law, KVL, KCL, and so on, we won't need to go to current division. Okay, so that's basically, you know, the quantities that we're looking for. And so we start down here, and we can say that F is equal to IT equals 2.5 amps, and therefore VF equals IF times RF, and we have 2.5 amps times 50 ohms, and that gives us VF at 125 volts. And so 125 volts for VF. So we move over here now. We're going to say that in this circuit up here, we know that if I write Kirchhoff's current law here, IT is equal to ID plus I. E. Should be E there. And we also know that because our D and our E went into making F, then this voltage right here is our F at 125 volts. So we're going to say that VD is equal to VE is equal to VF at 125 volts. We're also going to say then that IE by Ohm's law is equal to VE divided by RE. And that means 125 volts divided by 100 ohms gives us 1.25 amps for IE. So now Kirchhoff's current law at the node says that IT is equal to ID plus IE, or ID is equal to IT subtract IE, and we have 2.5 amps subtract 1.25 amps. Decimal in there. And we see then that these two equal resistors will have divided the current equally, and so that ID is equal to IE both at 1.25 amps. Now I have chosen here to calculate ID using Kirchhoff's current law. If we agreed that VD equals VE up there, I could have equally as well calculated ID using Ohm's law, right? And so either way, we're getting 1.25 amps through each of those branches. So IT comes in here. These two resistors are equal. The voltage drive across them are equal. The currents through them will be equal. Okay, they will divide the total current evenly. Now that's only because they are equal. Okay, so now we need to move up to the next circuit. And I guess really we want to say that we're moving that way. So now we have then ID right here. We know that value. We have IE right here. We know that value. In actual fact, we agreed that we know VD as well, right? Because it was equal to VE and F at 125, and so we can bring those values up to this circuit. And so what we want to do is say that in this circuit up here, that IB is equal to I5 in this branch right here, and that because RB and R5 came from RD, that is equal to ID. And so we have then VB is equal to IB multiplied by RB. And if IB is equal to ID, which we calculated below at 1.25 amps, then VB equals 1.25 multiplied by 50 ohms, and that gives VB at 62.5 volts. And if we move up to the original circuit now, here we see that R3 and R4 went into making RB, so we can say that V4 is equal to VB at 62.5 volts. And that was the answer to part C. Okay, so in addition now, we also are going to say that right here, this current is IE, and so we want to say that I2 is equal to IC is equal to IE. And we can say now that the voltage here is VC, and VC is of course equal to, by Ohm's law, IC times RC. And so for VC now, IC is equal to IE, which we calculated at 1.25, so 1.25 amps, times RC, which is 80 ohms. And that gives us VC is equal to 100 volts. And so we have VC here at 100. Now, when we bring that up to this circuit here, right, because our 6 here and our A went into making our C, then we're going to say that V6 is equal to VA is equal to VC at 100 volts. And that helps us do the two remaining calculations. And so because we know V6 then, we can say now that P6 is equal to V6 squared divided by R6. And that's simply because P is V squared divided by R, and that should be P6 there. So we have the 100 volts for V6, and we're going to square that and divide by the value of R6, which is 160 ohms, and come up with P6 is equal to, if you do that calculation, 62.5 watts. Okay, so that is the answer to part D. Now the remaining piece that we want is I7, and remember that I7 is here, and so it's I7 and I8 in that branch right there. And because R7 and R8 went into RA, we can say that IA is equal to I7. Okay, so squeeze that up here now. IA is equal to I7. And from Ohm's law, we know that, of course, IA is equal to VA divided by RA. And we wrote down here that VA is VC at 100 volts. And so now IA becomes 100 volts divided by RA. And RA, of course, from this circuit here at 160 ohms. And that gives us IA is equal to 0.625 amps. And so we're going to write therefore I7 is equal to 0.625 amps. And that is then the answer to part E, which is the last part of the question. And so now, normally for these things, we want to concentrate on answering, just the things we've been asked to find. So gear your circuit analysis towards that. With respect to a VIR chart or a PVIR chart, you can continue on for this circuit and fill up the whole thing if you wish. The calculations that you come up with should agree with the answers that are provided here.